GameSide.com. GameSide.com.
Hi diddly diddly! Welcome to the lesson on the heap data structure. A heap implements a very fast priority queue. A normal queue is FIFO, first in, first out. New items always enter at the back of the queue and must wait behind all items. A priority queue allows new items to insert at the back, middle, or even front of the queue when it has a high priority. If life were fair, we would only need a normal queue. But life ain't fair. Some of us wait in line longer than others, and that is because of priority queues. Heap data structure. Heaps are based on binary trees. The highest priority item is in the root of the binary tree. To the left is a max heap. 90, the highest priority, is in the root. 10, the smallest priority, is in the leaf. A large online video game would use a priority queue, so system administrators and game monitor commands take priority over player commands. Waiting in line at a crowded nightclub is a priority queue. Those known to spend a lot of money get to move to the front of the line. A defense tracking system on an F-22 fighter jet is a priority queue. The jet faces many adversaries. You want to alert the pilot to the highest priority dangers that face his airplane. Many people don't know this, but bank customer service is a priority queue. What call is answered first when you call the bank? Is it the person that called first or the person with the most money? Banks and many other businesses answer your phone calls in a priority queue where their best customers get answered first. There is a big difference between a binary search tree BST and a heap. Large values in a BST are on the right, small values go to the left. Large values in a max heap are at the top of the heap or the tree, and small values are at the bottom of the heap or the tree. A binary search tree or BST, any node with key value of x, all keys in the left subtree are less than the value of x, and all the keys in the right subtree are greater than the value of x. Heaps kind of rotate this 90 degrees. The large values go towards the top, the small values go to the bottom. A heap tree has 3 features. Number 1, it's complete. All non-leaf levels are full, and the leaf level is filled left to right. There are no gaps or empty spots in a heap binary tree. It's always balanced. If you look at level 0, it's full. There's only one possible node that can go on it. That node is full. Here's a full level 1. At most, there could be 2 nodes on this level of the tree, and they are both occupied. Here is a full level 2. 2 to the second power is 4. At most, there could be 4 items on this level, and this level is full. That's what I mean by a complete binary tree. All the non-leaf levels are full. The leaf level fills up left to right. As items are added to this heap, they will be filled in left to right. A heap tree has 3 features. The second feature of a heap tree is it's built from a one-dimensional array. We are going to map our binary tree directly onto a one-dimensional array. The root, or level 0, is at slot 0 in this example. Level 1 then gets slots 1 and 2 of the array. Level 2 gets slots 3, 4, 5, and 6, and so on down the line. This is a standard mapping of a binary tree to a one-dimensional array. In order to do this, you must know the formulas. The left child is at 2 times index plus 1. The right child of a parent node is at 2 times index plus 2. And even the parent can be calculated. Parentheses, index minus 1, end of parentheses, divided by 2. You can move up a binary tree as easily as you can move down a binary tree. And these parentheses are very much required. A heap tree has 3 features. Number 3, each node satisfies the heap condition. Every parent node key is greater than or equal to the keys of its children. If you look very carefully, this parent 90 is greater than the two children, 80 and 70. If you look carefully, this parent node 80 is greater than 75 and 50. This parent 70 is greater than 15 and 40. In a heap, larger keys to the top of the tree, smaller keys to the bottom of the tree. BST moves larger keys to the right and smaller keys to the left. The heap binary tree is kind of a BST rotated 90 degrees. See this 90? In a BST, it would be sitting over here. If you rotate 90 degrees, it comes to the top. Arrays are better for heaps. Mapping a heap binary tree to a one-dimensional array is actually the preferred way to do it. You don't need to or even want to implement a heap binary tree using references or pointers. Number one, it's easy to size the binary tree to a one-dimensional array. Pick the closest power of 2. 2 to the 10th equals 1024. If you want to create a priority queue with about 1,000 items in it, allocate 1024 slots in the one-dimensional array. What if you need to store up to 4,000 items in your priority queue? 2 to the 12th is 4096. Well, 4096, that array will hold a 12-level binary tree. Number 2, it's easy to move up and down. Better than links, no parent references are needed to track. When you map a binary tree to a one-dimensional array, it's easy to move down the array, and it's easy to move up the array. No references, no parent links are needed. Number 3, there's no wasted RAM. The tree is complete and balanced. You don't have to worry about an unbalanced tree and wasting space in the one-dimensional array. Heap binary trees are always balanced. They're always complete. There's no need to worry about unbalanced trees and wasted space in a one-dimensional array. All this depends on you memorizing the formulas. With the root at index 0, the left child can be calculated as 2 times index plus 1. The right child is 2 times index plus 2. And the parent, when you need to move up the heap, can be calculated as parentheses, index minus 1 into parentheses, divided by 2. Those parentheses are required. Heaps are weakly ordered. There's no BST in order traversal. You can't even tell which side of a tree 15 will be on. If you are searching for 15 here at the top of the tree, you don't know whether you should go this way or that way. There is some slight or weak ordering. Each path, root to leaf, is an ordered list. If you start at 90 and move down the tree 80, 50, 20, that is an ordered list. We will use this order to sort in a later slide. Weak order means follow any path, root to leaf, and they are in order. Start at 90, go to 80, 50, 20. That is an ordered list of those 4 items. Start at 90, go to 70, go to 15. Ordered list from there, but it's weakly ordered because at 90 you don't know which direction to go to get to 40. Do you go this way to search for 40 or do you go this way to search for 40? A find of 15 would have to be a brute force order of n search. Left to right of 90, no way to tell. If you're going to search for 15, you're going to have to go through the entire array looking for 15 and finding it there. That is an order of n search. Heap priority queues are fast. As we look at the insert and remove options, notice how they work at order of log n speed. Heap binary trees are always balanced. They always perform at order log n speed. Heaps can also be used in a very fast sort algorithm. The only thing a heap does not do fast is a find of a specific item in the priority queue. Since heaps are weakly ordered, a find is order of n. If I wanted to find the item 10 in this priority queue, I'd start at position 0 and scan the whole thing until I find item 10. Heap remove. Remove the highest priority item from the front of the queue. A normal queue is FIFO, first in, first out. A priority queue removes the highest priority item first, and in a heap, that is always the root. I'm starting with a blank tree in an array to make a significant point. The tree on the left, this thing right here, is a visualization of the heap to show you how a heap works. It is not real. The array on the right is how a heap is created and stored in RAM memory. This is the more real representation of the heap. The tree that is drawn here is for illustration purposes only. We are not storing a heap binary tree using references and pointers. We are storing the heap binary tree in a straight up array. Heap remove. It takes the highest priority item off the queue. This can be done in 3 steps. Step 1 is remove the root. Step 1 should be blatantly obvious. The root of the heap, 90, contains the highest priority item and it should be removed. I've stored this 90 in a temp variable so it can be returned when the procedure is completed. The 90 can now be removed from the heap. Step 2 of the remove process is move the last node, the far right leaf, into the root. With the root vacant, you might assume one of the root's children, 80 or 75, would move up and take its place. That would be wrong. What we're going to do is move up 30, the last leaf, the far right leaf, to make it the new root, maybe just for a split second. The last leaf is the only node that will not have a domino effect that causes shifting or restructuring of the tree. The 30 moves up to replace the root. Look at the array. No gaps, no shift, no restructure. I picked up the 30 that was here and moved it up into the root there. Notice how the tree is still complete. That is a heap requirement. All non-leaf levels are still full. Leaf level is filled in left to right. This is a balanced tree. Step 2 is done. On to step 3. Moving the last leaf is the only item that does not require a restructured tree or a shift. If I had moved one of these items, I would have to shift the other items to take its place. 30 can just move up without any shift whatsoever. Step number 3, trickle the last node down the tree until it's below a larger node and above a smaller node. What? The 30 clearly violates the heap condition. It must trickle down the tree to where it belongs. Swap 30 and 80, the largest child. Note 75 cannot swap. It is not larger than 80. As the largest value left in the queue, 80 should become the new root. 30 will compare against its largest child, and 30 and 80 are out of order. 30 and 80 need to swap. Now, why did we pick 80? Because 80 is larger than 75. You compare 30 to the largest child, and that's 80. 30 and 80 just changed positions in the array. However, the 30 still violates the heap condition. It must trickle down the tree to where it belongs. We are still in step 3, the trickle down. The trickle down can take many steps. Note, 50 cannot swap. It is not larger than 70. Why did we compare 30 and 70 and not 30 and 50? Because 70 is larger than 50. You always compare the node that's trickling down to the largest child. Why do you compare to the largest child? Because the value 70 should become the parent of 30 and 50. That's the heap condition. 70 is the one that has to move up, so it's the parent of 50 and 30. Finishing step 3, the trickle down of the node. Time to stop. 30 meets the heap condition. It's larger than its children. It is where it belongs. At this point, the tree is a valid heap. Time to return the temp variable, the 90 that started all this. Remember, we're removing the largest item from the heap. That's 90. It's time to send that 90 back to the caller. 30 is done. Why is 30 done? Because it's larger than 25 and 10. The last thing we did here was 30 and 70 swapped. 30 and 70 changed places in the array. Note, it took only 3 swaps to move 30. Worst case on this tree would be 4, or the number of levels of the tree. That is an order of log n algorithm. If I have a 10 level tree, I might have to swap 10 times when I trickle down. Wrapping up the heap remove of the highest priority item 90 in the queue. Notice 80, the new high priority item, is now the root. The 30, which was the last leaf in the array, is now moved to a good position, and the values in the array now reflect their position in the tree. 30 used to be right here. It moved up and trickled down to this position. In order to do that, 30 had to move up to here. Then we swapped here and we swapped here. And 30 ended up in slot 3 of the array, exactly where it should be. As long as this node is larger than its two children, it's in the proper spot. Let's do a second heap remove in 3 steps. Step number 1 of removing an item from the heap is to remove the root. The root contains the highest priority item in the queue. It's time to take it out. Step 1 should be blatantly obvious. The root of the heap 80 contains the highest priority item, and it should be removed. I've stored 80 in a temp variable so it can be returned when the procedure is complete. The 80 can now be removed from the heap. Step number 2 of the heap remove algorithm. Move the last node, the far right leaf, into the root. With the root vacant, you might assume one of the root's children, 70 or 75, would immediately move up. That is wrong. Move 10, the last leaf, the far right child, to make it the new root, just for a split second. The last leaf is the only node that will not have a domino effect that causes shifting or restructuring of the tree. Remember, a heap tree needs to be complete. All the nodes have to be full. If I move one of these nodes, it's not full. If I remove this node, the heap remains full or complete. Still moving that last node up, the 10, which was right here, moves up and takes over the root. Look at the array. There are no gaps in this array. When the 10 moved up from this position to that position, no blank spots opened up in the middle. The tree is still complete. This is a heap requirement and balanced. Step 2 is now done. On to step 3. Moving the last leaf is the only item that does not require a restructured tree or a shift. Heap remove. Step number 3. Trickle the last node down the tree until it's below a larger node and above a smaller node. The 10 at the root clearly violates the heap condition. It must trickle down the tree to where it belongs. Which way will it go? 75 is larger than 70, so I'll compare 10 to 75. Swap 10 and 75, the largest child. Note, 70 cannot swap. It's not larger than 75. What would happen if we move this 70 up to here? This 70 would violate the heap condition because it would be the parent of 75. So 75 is the one we have to compare, the larger of the two children. As the largest value left in the queue, 75 should become the new root. 10 and 75 just swapped positions. The 10, however, still violates the heap condition. This 10 is not in the proper spot. It must trickle down the tree to where it belongs. Swap the 10 and 40, the largest child. Once again, 10 looks at both children, 15 and 40, and swaps with the larger of the two. Note, 15 cannot swap. It's not larger than 40. The value 40 should become the parent of 15 and 10. That's the heap condition. 10 and 40 just swapped. 10 is done. It's now in a leaf level. I'm finishing or completing the trickle down of 10. Stop. 10 is now a leaf. It's where it belongs. You can't trickle down farther than a leaf. At this point, the tree is a valid heap. Time to return the temp variable. Remember, all of this started when we removed 80 from the priority queue. We are completing that process now. At this point, the tree is a valid heap. Time to return the temp variable and send 80 back to the caller. Note, it took 3 swaps to move 10. Worst case in this tree would be 4, the number of levels of the tree. This is an order of log n algorithm. I had to swap 10 1, 2, 3 times. The worst case on a 4-level tree would be 1, 2, 3, 4 swaps. This is clearly an order of log n tree. The maximum number of swaps you'd have to do is the number of levels of the tree. Wrapping up the heap remove of the highest priority item 80 in the queue. Notice 75. The high priority item is now the root. The 10, which was the last leaf in the array, has now moved to a good position, and values in the array now reflect their position in the tree. 10 started down here. It moved up to the root. It swapped with 75 and moved to here. It swapped with 40 and moved to there. That's the trickle down. Heap insert. Place a new item in the queue at its priority position. A normal queue is FIFO. A new item is placed at the rear or back of the queue and it's done. A priority queue may start a new item at the back but must move it to the proper position the item priority requires. It is possible that it winds up at the front. I'm starting with a blank tree and array to make a significant point. The tree on the left is a visualization of the heap to show you how the heap works. This is not the real representation of the tree. The array to the right is how a heap is created and stored in RAM memory. It is more real. We will be placing items in our 1D array and trickling them up and trickling them down through the array. Heap insert requires just 2 steps. Number 1, we're going to add a node as the far right leaf at the end of the array. That's curious. New items insert as a far right leaf at the bottom level of the tree. New items are inserted as a far right leaf for a good reason. Looking at the array, no shift is required, and it keeps the tree complete. This is the position in the array where I can put a new item without moving any of these items. That is a good thing. We do not want to have to shift or reshuffle these items in the heap. This is where a new item should start. When a level fills up, it will drop down and create a new level, which may have happened when 25 was inserted. We're going to fill up this level completely before we drop down and insert a new level of this tree. You fill up all the upper levels of the tree first. Insert 60. No shift needed to place new item in slot 9. Step 1 is done. Go on to step 2. Curious. See this 60? That's the new item we're putting into our heap. Put it at the end of the array. That is the one spot in this array where you can insert it without shifting anybody else out of the array. Always start the new items at the end of the array. Remember the heap condition. A parent must be larger than a child. In many ways, insert is easier than remove. You only have to look at one parent, not 2 children, for the heap condition. Step 2 of the heap insert is trickle up the node until you find the position where the new node is smaller than its parent. When we did a remove, we did what's called a trickle down. When we do an insert, we'll do what's called a trickle up. Compare the new item 60 to the parent 50 and trickle up when the new item is bigger. 60 is larger than 50. We need to compare 60 to its parent 50. Since the heap condition says 60 must be the parent of 50, swap positions in the array. Once again, notice no shift is required, just a simple calculation of the parent location and a compare. 60 is in position 9 of the array, or index 9. 9 minus 1 divided by 2 equals 4. Compare 60 in slot 9 to 50 in slot 4. When they're out of order, swap the two. Swap 50 and 60, then compare 60 to its new parent 80. The new item 60 will move up until it finds a parent larger than itself. 60 in position 4 has to compare to 80 in position 1. Completing the trickle up of the node until you find the position where the new node is smaller than its parent. We're going to stop. The parent is bigger. The heap condition is met. 60 is not greater than its parent 80. Stop the trickle up. The new item 60 is where it belongs in the tree and in slot 4 of the array. Only a very high priority item makes it far up the tree. For example, if we were inserting 95, it could make its way to the top. Clearly 60 is in a proper spot. It's above 50 and below 80. That's the heap condition. 60 and 80 were not swapped. 80 is larger than 60. It's done. Wrapping up the heap insert of the new item 60 in the queue. Notice 60 was inserted before 50. That is what makes it a priority queue. The 50 is now a leaf and must wait behind 60, the higher priority item, in the tree, array, or queue. Let's do another heap insert in 2 steps. The 2 steps are: number 1, add a node as the far right leaf at the end of the array. Step number 2 is trickle up the node until you find the position where the new node is smaller than its parents. New items are always inserted as the far right leaf. The far right leaf is at the end of the one-dimensional array right here. New items are inserted as the far right leaf for a good reason. Looking at the array, no shift is required to insert a new item at the end. It keeps the tree complete. Shifting items is slow. When a level fills up, it will drop down and create a new level. Note how an insert touches very few existing tree items. Inserting a new item here does 2 important things. Number 1, it makes sure the tree is complete. Number 2, it doesn't require us to shift the rest of the items in the array. Let's complete the adding of the far right leaf at the end of the array. Compare the new item we're inserting, 45, to the parent 60 and stop. No trickle up. The parent is bigger. What did I just do here? 45 is the new item. I need to check the parent 60. How do I check the parent 60? 45 is in position 10. 10 minus 1 divided by 2 is 4. I need to compare this 45 here to that 60, its parent, in slot 4. That's great. Low priority items do not even trickle up. We're done. This is a very fast algorithm when you insert a low priority item into the queue. It starts as a far right leaf, and if it doesn't need to trickle up, you're done. Let's insert a third item. Heap insert is 2-step algorithm. Number 1, add a node as the far right leaf at the end of the array. Step number 2 says trickle up the node until you find the position where the new node is smaller than its parent. We're going to insert our new item right here as the far right leaf node, which means it will occupy slot 11 in the array. New items are inserted as the far right leaf node for a good reason. Looking at the array, no shift is required to insert a new item at the end of the array. It also keeps the tree complete. Shifting items is slow. When a level fills up, it will drop down and create a new level. Note how an insert never touches items to the left of 90. We're going to do this entire insert and never touch anything on this side of the tree. Insert 85. Completing step 1 of the heap insert. No shift needed to place the new item in slot 11. There's 85. It goes in at the end of the array. Step 1 is now done. We can move on to step 2. Remember the heap condition. A parent must be larger than a child. In many ways, insert is easier than remove. You only have to look at one parent, not both children, for the heap condition. The only question we have now is 85 larger than its parent. I think you know the answer to that. Step number 2 says we need to trickle up the node until we find the position where the new node is smaller than its parent. We're going to compare 85 to its parent 15. We need to compare the new item to its parent. Compare the new item 85 to its parent 15 and trickle up when the new item is bigger. The heap condition says 85 must be the parent of 15. Swap positions in the array. No shift is required to do this, just a simple calculation of the parent location and a compare. 11, which is 85's position, minus 1 divided by 2 equals 5, says we should compare slot 11 to slot 5 in the array, and these are clearly out of order. We're still doing the trickle up here. 85 and 15 just swapped positions. 85 has to be the parent of 15. Now we need to compare the new item to its parent. The 85 clearly violates the heap condition. It must trickle up the tree to where it belongs. We swapped 85 and 15 first, then we compare 85 to its new parent 75. The math is easy. 85 is in slot 5 or index 5. 5 minus 1 divided by 2 is 2. We need to compare slot 5 to slot 2. The new item 85 will trickle up until it finds a parent larger than itself. 85 and 75 need to swap. The 85 clearly violated the heap condition. It must trickle up the tree to where it belongs. Swap 85 and 75. 85 and 75 just swapped right there. After that's done, compare 85 to its new parent 90. 85 is now in position 2. 2 minus 1 divided by 2 equals 0. Compare 85 to the value in position 0 of the array. The new item 85 will trickle up until it finds a parent larger than itself. Still in the trickle up, the parent is bigger. The heap condition is met. 85 is not greater than its parent 90. Stop the trickle up. The new item 85 is where it belongs in the tree and in slot 2 of the array. Only very high priority items make it far up the tree, and this one nearly made it to the root. 85 is a high priority item, was inserted into the queue very far up into the queue. High priority items rise to the front of the queue. Both trickle up and trickle down do at most one swap per level of the tree. This is order log base 2 of n, and of course big O drops the 2 and it becomes an order of log n algorithm. Let's say we were building a huge online game like Pokemon Go. Hundreds of thousands of game commands are in the priority queue of Pokemon Go. Well, 2 to the 17th power is 131,072. Pokemon Go can insert and remove from its heap with just 17 tiny little swaps. That's fast. Again, there's 100,000 commands coming in every second. Every second you've got to execute those commands with a priority. It only takes 17 swaps to insert something into a large priority queue. Heap sort. Build a heap and tear it down to sort the data. A heap is weakly ordered. That means there's no way to do a find of an item without doing a time-consuming order of n linear search of the heap array. Also, no BST in order traversal that visits the data in a sorted order. But if you are willing to remove all the items from a heap, destroy the heap, the data will come out in sorted order. The heap sort algorithm is: insert the unsorted data into a heap, remove all the data from the heap, and it comes out in a sorted order. Here is a list of unsorted data. Heap insert this unsorted data into a heap. After you're done inserting it into the heap, remove each item from the heap and it'll come out as sorted data. Heap sort. Heap sort has 2 loops. This first loop is going to spin over and over and over and call insert. It's going to insert, 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 insert each of the items, building up the heap. Then the second loop is going to spin and remove, remove, remove. I'm going to remove all the items out of the heap in a sorted order. Heap sort requires 2 loops. The first loop will go through all unsorted items in the array data and insert them into the heap. So it will insert 70 and then insert 50, then insert 90, and so on. The second loop will spin the same number of times and remove all the items in sorted order. The 90 will be pulled out, the 80 will be pulled out, the 75 will be pulled out. Tracing the code, J will start at 0 and we will insert data sub J, which is the value 70. Insert 70, easy. The first item in the heap is always the root. Note the 70 is placed in slot 0 of the array. Know the 3 formulas for accessing a one-dimensional array heap. The left child is 2 times index plus 1. The parent is parentheses index minus 1 end parentheses divided by 2. And the right child is 2 times index plus 2. Know the formulas to understand how insert and remove work. Insert 15. Adding a new low priority item, no trickle up is needed. J now equals 1. Insert data sub J, which is the value 15. The 15 will be pulled out of the array data and inserted into the heap. In this case, it's a very simple insert because 15 has a lower priority to 70. We don't have to do anything except insert 15 at the end of the heap. Insert of a high priority item will require a trickle up. 90 is greater than the parent 70. There's going to be some swapping here. In the loop, J is now 2. Insert data sub J says insert 90 into the heap. We pull 90 out of our unsorted data and insert it right here. New items always go at the end of the heap. After they go at the end of the heap, we trickle up. 90 is greater than 70. It has to go up. Continuing the insert of 90. The swap of 90 and 70 occurs, and the insert of 90 is complete. Note the swap in the array. What just happened here? 90 started at the end of the heap. It swapped with 70 and became the root. That's what a heap insert does. New items go at the end and trickle up until they reach the point they belong in the heap. 90 is now in the heap. Insert 80. Insert of a high priority item will require a trickle up. 80 is greater than the parent 15. It looks like we're going to do a swap. As far as our loop goes, J is now 3. Insert data sub J. That's the 80. Take this 80 out of the unsorted data and insert it into our heap. 80 is greater than 15, so we're going to have to swap it up the tree. Continuing the insert of 80, the swap of 80 and 15 occurs, and the insert of 80 is now complete. Note the swap in the array. 15 and 80 just swapped positions in the array. 80 was higher priority than 15. It has to trickle up. Insert of 50. Adding a 50, which is less than the parent 80, no trickle up is needed. This is an easy case. Data sub J is 50. Insert this item into the heap. The 50 inserts at the end of the heap, at the end of the array. That's where all new items go. They go at the very end of the array. You look at the parent, which is 80, and no trickle up is needed. 50 is less than 80. Insert of 75. Insert of a high priority item will require a trickle up. 75 is greater than the parent 70. There's going to be a swap. Once again, we're still spinning in this loop. We're going to call insert of data sub J, which went up by 1, and that's going to select 75 for inserting into the heap. 75, like all new items, goes in at the end of the heap, at the end of the array right here. We then trickle it up by looking at its parent. Turns out 75 is greater. Time for a swap. Insert 75. The swap of 75 and 70 occurs, and the insert of 75 is complete. Note how the numbers swapped in the array. 70 was here, 75 was there, those two swapped. 75 has a higher priority, it will swap. 75 will look at 90 and not swap. Insert 40. Adding a 40, which is less than the parent 75, no trickle up needed. By the way, that is an order of 1 insert of 40. The heap object tracks the last used slot in the array and places 40 there. A simple check against the parent and the insert is done. J went up. Insert of data sub J says insert 40 into the heap. Grab this 40 and insert it into the heap. The new items always goes at the very end of the array, at the end of the heap. We look at our parent and decide whether we should trickle up. The answer is no. 40 is less than 75, no trickle up is needed. This is order of 1 because we only had to access one slot of the array, position 6. The first loop has built the heap from the unsorted array. When this loop came back up, J++ incremented J less than the size became a false statement. When that became false, this loop exited and it went down to the second loop. Time to execute the second loop. The first loop is done. Time to execute the second loop. For J equals a size minus 1, J greater than or equal to 0, J minus minus this time. We're going to go backwards through the data on the second loop. The second loop will now destroy the heap so it can output the data in sorted order. The second loop spins backwards, so the large values removed first goes to the end of the array. Call the remove method to take the highest priority item 90 from the queue. Requires the far right leaf to move up, the 40, and trickle down to its proper position. The second loop spins backwards, empties the queue, and fills data from the end of the array. What does that mean? We're going to start at the end of the array and remove an item from the heap. That remove will pull the highest priority item, 90, off the heap. Remove the root and store it at the end of the array. Take it out and put it at the end of the array, or position J. Again, we're moving backwards. Watch what this 40 does. The 40 moves up to replace the 90. Remove continues. The far right leaf 40 replaces the root. The 40 will now trickle down to its proper position. Notice the heap array. No gaps ever in the array. 40 was moved from the end to the beginning. So the 40 that was here, or in position 6, moved up to replace the 90 and is now there. Trickle down says compare the 40 and 80, and the 40 should trickle down. Now, why did 40 compare to 80 and not 75? Because 80 is larger than 75. Trickle down says look at the largest child, compare yourself, and trickle down if you're smaller. Remove continues. 40 and 80 swapped in the heap. You can see that they swapped in the array also. After that swap occurs, the far right leaf 40 is compared to the largest child 50. The 40 will now trickle down again to its proper position. Compare the 40 and 50. 40 has not finished the trickle down. It's going to have to swap with 50. Notice the heap array. No gaps ever in the array. No shifting as 40 moves down. 40 is going to compare to 50 and swap if they're out of order. And that's exactly what will happen. The remove of 90 is now done. The former far right leaf 40 trickled down to its proper position. 40 started here and moved down to here and then down to here. 40 is in a leaf. It is now done. Notice the heap array. No gaps ever in the array. No shifting as 40 moves. The 90 was returned and assigned to the slot at the end of the array. This is finally the complete or the finish of the 90. When 90 is finished being removed, it's returned to data sub j and gets inserted at the end of the array. Call remove method to take the highest priority item 80 from the queue. Requires the far right leaf 70 to move up and trickle down to its proper position. The second loop spins backwards. It empties the queue and fills the data array from the end of the array. We're spinning in this loop. We call remove a second time. It will remove 80 from the heap and send it back to the sorted array. Remove the root and store it at the end of the array. Remove continues. The far right leaf 70 replaces the root. The 70 that was sitting right here moved up and replaced the root. The 70 will trickle down to its proper position. Notice the heap array. No gaps ever in the array. 70 was moved from the end to the beginning. The 70 that was in slot 5 moved up to the root position. Compare 70 and 75 and trickle down because this lower priority item cannot be the parent of a high priority item. Again, why did we compare it to 75 and not to 50? Because 75 is the largest child. The remove of 80 is done. The former far right leaf 70 trickled down to its proper position. 70 made it down to here. 70 is a leaf. The trickle down is done. Notice the heap array. No gaps ever in the array. No shifting as 70 moves. The 80 was returned and assigned to a slot at the end of the array. 70 and 75 swapped, but we did not have to shift any data. The 80 that was removed is assigned to data sub j. J is pointing towards the end of the array. 80 came up near the end of the sorted data. Call the remove method to take the highest priority item, 75, from the queue. Requires the far right leaf, the 40, to move up and trickle down to its proper position. Notice the second loop. Look at what it does. J minus minus. So J is moving from 6 to 5 to 4. J moved 90 to the end, and then it moved 80 here. And 75 will go in at 1 less. We're taking 75 out of the heap and assigning it to the end of the data array. Remove of 75 continues. The far right leaf 40 replaces the root. The 40 will now trickle down to its proper position. During trickle down, compare it to the largest child 70. We're still in the middle of removing 75. The 40 that was right here moved up to the root. 40 now has to trickle down. 40 has two children, 50 and 70. Compare 40 to the largest of the two children and trickle down in that direction. The remove of 75 is done. The former far right leaf 40 trickled down to its proper position. Notice the heap array. Notice the heap array. No gaps ever in the array. No shifting is 40 moves. The 75 was returned and assigned to slot data sub j of the array. The remove of 75 is done. The 75 then gets assigned to data sub j. Data sub j says put it in the end of the array. We're still spinning in this loop and calling remove. Call remove method to take the highest priority item, 70, from the queue. Requires the far right leaf, 15, to move up and trickle down to its proper position. Remember, the second loop does a j minus minus. So j is moving 6, 5, 4, 3. 70, when it gets finished being removed, will go in position j of the sorted array. Remove the root and store it in index j of the array. The remove of 70 continues. The far right leaf 15 replaces the root. The 15 will now trickle down to its proper position. During trickle down, compare it to the largest child, in this case 50. 15 was removed from the bottom of the heap and put at the top of the heap into the root. 15 will now trickle down by looking at its largest child. Why are we going this way? Because 50 is larger than 40. Comparing 15 and 50, we have to swap those two to trickle down. The remove of 70 is now done. The former far right leaf 15 trickled down to its proper position. 15 is a leaf, we're done. 15 and 50 swapped positions, both in the heap and in the array right there. Notice the heap array. No gaps ever in the array, no shifting as 15 moves down. The 70 was returned and assigned to slot data sub j of the array. As the data comes out of the array, it gets assigned to slot j and is in a sorted order. Still spinning in this loop, it's time to remove 50. Call the remove method to take the highest priority item left in the queue, 50. Requires the far right leaf 40 to move up and trickle down to its proper position. You always take the last item in the heap and move it up to the root. The second loop will remove all items from the heap, and we're getting close to having that done. Remove of 50 is done. The far right leaf 40 replaces the root. Boom. 40 was here, it moved up to that position. The 40 will not trickle down. It's already greater than 15. When we compare 40 and 50, no trickle down is needed. The remove of 50 is complete and will assign 50 to data sub j. There's the 50 at data sub j. Remove the root 40 and store it at index j of the array. So 40 comes out of the heap and is going to be replaced by 15. The remove of 40 is done. The far right leaf 15 replaces the root. The 15 will not trickle down. It's the only thing left in the heap. There is nowhere to trickle. Notice also my array. 15 is the last item left in the array. The remove of 40 is done and it's assigned to data sub j. Call the remove method to take the highest priority 15 from the queue. There is no leaf to promote, so this deletes the heap and completes the heap sort algorithm. The call to remove of the last item just takes it out and assigns it to data sub j. J is moving backwards, so j is now 0. 15 goes into slot 0 of the array, and you can see I have sorted data. I went from this unsorted data to this sorted data. Kind of jarring that the tree disappears, but that's how a heap sort works. Build a heap from unsorted data, then destroy it to extract the sorted data. Heap sort is an order of n times log n algorithm. Why? The first loop spins n times and calls insert, which is an order of log n algorithm. This loop spins n times. Each call inside that loop calls an order of log n algorithm. The second loop spins n times and calls remove, which is also an order of log n algorithm. This loop will spin n times, and each time during that loop it will call remove, which is order of log n. Together the two loops are order of 2 times n times log n, but big O drops the 2, so heap sort is an order of n times log n algorithm. Heap sort is a very fast sorting algorithm. It's also logically quite simple. If you understand how heap insert works and how heap remove works, Heap sort is a fairly simple algorithm.
Ginside.com.